Hello everybody, this is the third video of this series. Will be the last video of this series. And what we are talking about first, in the first video, I'm gonna show you some card here. I don't know, we talked about artificial intelligence evolution and supply chain logistic crisis, how artificial intelligence evolution can help solve the supply chain logistic crisis, okay? And in the second video, I believe that will appear in the some place here, some card for the second video, okay, appear. We talk in detail, we talked about the implementation of simulation based on representation by rules methodology to plan port logistics operation, okay? And finally, in the third video, we'll talk about how we can automatically generate rules, and these rules can be applied in many contexts for the supply chain. It will be very interesting and important. So, what's happening exactly on supply chain logistics? Here we have this Washington Post report, and these are talking about the number of ships that are waiting to dock at Southern California ports. As you can see here, we have a great increase in the container ships onshore offshore. So these are ships waiting to dock here to be loaded or unloaded cargo in these ships. Okay, and what is the problem with this? Well, the freight rates will increase, and as you have a query here, we have a query of ships in many places, and this is not good for everybody, since the price of everything will be higher. Okay, and this is a very important situation that we can have here, people. As you can see here, we have, for example, yard, and these are flat yard. Okay, so we don't have stacks here, and here we have a container blocking these ones, or a container blocking these ones. If you want to access these ones, you have to move this at first. In the second video, we have a same situation in the container ship, and the yard can happen also. So how we can deal with this? And this is a big trouble. So the most often solution for this problem is to organize cargo in stacks. For example, use this solution to organize cargo in a container ship, or to organize cargo in a port yard here. Or, for example, you can organize cargo inside a container ship using stacks. Also, in a picking area, warehouse, we can organize the cargo using stacks. Okay, so here we have another places where we can use stacks, warehouse storage area, or, for example, how we are using stacks to organize cargo in a truck. Okay, so what's the problem to use stacks? Many times we can have blocking, we still have blocking cargo or containers when we use stacks. So what is the contribution of this talk is how we can generate automatic procedure to create suggestions of sequences to load cargo in a grid space, in a regular space. So imagine that you have a space and can organize cargo in a regular space. Okay, and what are the two constraints that we should be careful to build a procedure that creates a feasible sequence? For example, we should not allow one cargo. We should allow one cargo for each space. We can have 2 or 3 or more cargo in the same space at the same time. And we can allow floating objects. So each object, each container should have support, or it's in the bottom. Okay, so blue it's okay, blue cargo or blue containers or blue boxes are okay here, but the red ones are not because they don't have support. They are just floating. They are just flying. Okay, and what is the problem? We can start to fill a 2D space, and here we're gonna consider this space have any columns and any rows, and here we start to fill this space from the top. It's not right. It's bad because we are not respecting this constraint. And how we can avoid an infeasible sequence, it's much interesting, and we can this Flatway inside. So imagine that we start from the base, from the possible places where we can put the cargo. Since we have any rows, any columns, we can start. We have any possibilities here. We start from the middle, and after that, after we position first position our container in the point 1, we can already again we have this any possibilities to put the second cargo, and we can choose n this number of possibilities to fill this space until we reach the last row. So in the last row we have any factorial possibilities to fill this to create sequence. So we have this number of possible feasible sequences to fill this regular space. So as you can see, we have many possibilities of a sequence. Okay, we can also use a special case of this insight. We have the Huawei to fulfill this space. So since we started to put containers in one column, we should finish. So at first we have many we have any columns that we can start. We choose one, and we have our remaining possibilities. So we can combine different possibilities of rules. For example, we have this first combination. This is just one solution using the Huawei special case, and we have any factorial possible permutations to fill the space using columns, using this stack approach or the Huawei approach. So in summary, what we have this number of total possible sequence, but we can use this complete because you're gonna have some unfeasible solutions. Okay, but we have this second option, the Flatway. We have still a lot of possible feasible sequences, and the one is much less, is significantly lower than the two ones before that we showed before. But what is the main issue here? Many decision makers use this approach of build stacks or to separate an area for a certain cargo. Okay, this works well when we have a lot of space, or you don't have a lot of available space. And just to illustrate how many possible sequences we can have, this is a 4 row and 4 column space, and we will get the total number for each. The complete obviously will not you employ, but the Flatway and Huawei is feasible, will give feasible sequences, and we have about 4,000 million combinations of feasible sequence. And this number, I can tell you how about we have here million, billion, trillion, about 20 trillion of possible. Okay, but we have unfeasible possible sequence here, so this is not will be used. Okay, and what we created here, we adapted this approach to dimensional approach for a 3D space. This is the code in Python. as you can see here, it's very easy. Not very easy, okay, but it's compact, it's short, for sure. And this will create, using this second strategy, the Flatway strategy, this will create feasible sequences, and we're gonna randomly choose from this amount of possible sequence. But we tried not just small spaces, we try also spaces with many possible elements. And in this, as you can see here, the time to create a rule is very fast. Since we are not just create rule and operate at the same time, you can create and you have a database of rules or sequence to fill the space, the regular space, and you can in a second stage you can employ this database of sequence or rules to fill the space. So we can apply this on storage planning problem. We can generate many sequences and see what how these sequences are in terms of stability or in many other kind of terms. You just generate and see what is your interesting rule. So imagine that we are using the storage planning problem, and as we show in the second video, we can use this sequence to fill the container ship. We can call it then as a rule to fill the container ship, to load the containers inside the container ship. So we just talked in detail in the second video about the storage planning problem, which is about how we can organize cargo inside a container ship to minimize the number of movements, okay? And obviously, to don't produce this kind of situation, which we have a floating container, we have to just to move, if you are trying to move this yellow container, you should also move this orange container. Okay, so we can have some patterns here. We have some rules that we code manually. For example, this rule just trying to minimize the number of movements, and this another rule try to minimize the shipping stability. And we did this manually. And defining rules could be laborious and error prone. Okay, but instead of doing this, we have now an automatic generator of rules. So instead of doing this code, this extensive code can be replaced by just this. This code replaced, not just code and this code. Imagine that you are trying to code many possible rules to fill the container ship, and you should have more code. No, it's not necessary. This code can create any kind of valid rule for the container ship to fill or to load the container ship. And this is just, we can create a dictionary of loading rules. And okay, now we can avoid manually coding, okay? So we tested this for some instance here in the container ship. It's not just to fill the container ship. We have to consider that each container have a port destination, and each port will bring us some kind of problems. The blocking containers, we already talked this in the second video. I recommend again to see in detail the second video. Okay, here we have just a toy problem. Let's see this, and it's a small problem that we use to see what's happening when we created some sequence to fill the container ship. Here we have some two instances that we showed. This is the time to create a valid loading rule. Okay, so here we have two base, and three rows and 4 columns. Okay, this is the dimension for a very small container ship, but a true container ship will be greater than this, and obviously we will not show. And after this, what's the main point here of this work? We already integrated the rules generator with simulation optimization framework. So we get our work that we discussed in the second video, and also integrated with QuakeCrane's operation. We have here, we created the simulation, okay? But the true point here, I'm gonna show fast. We have this in the second work that I talked about in the second video, and we can do this. What's the difference here? We don't need a very extensive database coded manually. We can automatically generate a lot of rules, loading rules, using this procedure that we called GSFIRES, okay, 3D. And this is a very interesting approach, since we can create as many rules as we can, and not just this. These rules are not manually coded, and they are not error prone. And also we can create many rules and test and see, and will be very interesting and can be applied for many contexts: warehouses, port yards, container ship, storage planning. This is this approach I named as self-created rules simulation optimization framework. And that's it. Thank you for your attention. If you have any question, please leave some comments in the video, and I hope you find it very interesting and useful. I'm planning to talk about more in detail the codes I made in Python, but if I have many views or many comments or engagement, I will produce more videos about this. Okay? Thank you again, people, and see you in the next videos. Bye.